Hi everyone, I am Lahari T.R. Prasad. I am a second year student of CSE department in PES Institute of Technology and Management, Shimoga. So, in this video, I am explaining about encoding of machine instructions which is present in Module 1 of Computer Organization, that is basic structure of computers. So the content in this video are introduction, objective, prerequisites, encoding of machine instructions, and at the end a reference slide is present. So the objectives of encoding of machine instructions are machine instructions and program execution including branching and subroutine call and return operations, addressing methods for accessing registers and memory operand, assembly language for representing machine instructions, data and program controlled input or output operations. So far now we have studied that all instructions are one word length, that is 32-bit. So while studying encoding of machine instructions, we have checked the validity of this assumption. Also we study how assembly language is converted into machine instructions. And the prerequisites are parameter passing, additional instruction, logical shift, arithmetic shift, multiplication and division, logical instructions. Introduction to the encoding of machine instructions. The instruction that specifies the action that is to be performed by the processor. So, to be executed in a processor, an instruction must be encoded in a binary pattern. Such encoded instructions are referred to as a machine instruction. The instruction that use symbolic names and acronyms are called assembly language instruction. The assembly language instructions are converted into machine language using assembler program. So in this figure it shows an example how assembly language is converted into a compact binary pattern using an program assembler. So far now we have seen instructions that perform operations such as add, subtract, move, shift, rotate and branch. These are the instructions that may use operands of different sizes such as 32-bit and 8-bit numbers. Now opcode, OP code, that means the type of operation to be performed and the type of operands used may be specified using an encoded binary pattern. For example, if a word consists of a length 32-bit, here 8-bit is used for OP code and other is used for other operands such as source, destination operand, etc. Here there are some examples. Add R1, R2, move 24 of R0, R5, L shift R #2, R0, move hash and 3a, R1, branch greater than 0, loop. Here there is an explanation for an examples. Let us consider an instruction add R1, R2. Let us know how it works. This specifies the registers R1 and R2 in addition to the opcode. If the processor has 16-bit registers, then 4 bits are needed to identify each register. Then additional bits are needed to indicate that the register addressing mode is used for each operand. Let us move on to the next instruction. Move 24 of R0, R5. In this instruction, it requires 16-bit to denote the opcode and the two register, that is R0 and R5, that needs some bits to express, and the source operand uses the index addressing mode. In this instruction, move 24 of R0, R5, the index value is 24. And in that instruction, it requires 6 bit to choose the addressing mode, and the remaining 10 bits are left to give to the index value. So the next instruction is L shift R #2, R0. Here it requires an 18-bit to specify the opcode, the addressing mode and the register, and this limits the size of the immediate operand to which it is expressible is 14. So the next instruction is branch greater than 0 loop. Here it uses 8-bit for an opcode and a 24-bit are used for a branch offset. Here in this instruction, branch greater than 0 loop, since the branch offset is of 2's complement number, the branch must be 2 raised to 23 bytes of the functions. So to branch an instruction, different addressing mode has to be used, such as indirect. The branch that uses this known as jumping instructions. In all these examples, we came to know how much bits can opcode accommodate, and the other bits are used for source and destination operand as registers, and the remaining bits are used for other information. This is a diagram which shows one word instruction. As we can see, in the first column, 8 bits are used for specifying opcode. In the next two columns, that is source operand and destination operand, here each of them are assigned with 7 bits. In this, 7 bits identifies the addressing mode or the registers involved in it. And the fourth column is other information, and it uses 10 bits for other information. And the other information referred to as a index value. As we have seen in an example, move 24 of R0, R5. In that, 24 is referred to as an index value which can be stored in an other information. So this is a diagram representation of one word instruction of encoding of machine instruction into 32-bit words. As we know, in addition to the opcode, the instruction has to specify the source and destination registers, and along with that an addressing mode, etc. So what happens if we want to specify a memory operand using the absolute addressing mode in machine instruction? For example, if we have move R2, location, in this 18 bits denote the OP code, addressing mode and the register, and the 14 bit are used for the location, which is insufficient. So the best solution for this is, if we want to give complete 32-bit one solution, use second word. That means use two-word instruction as we have used one word instruction just like that. So by using the two-word instruction, we can specify a memory operand using the absolute addressing mode. So this is a figure which shows two-word instruction of encoding of machine instructions into 32-bit word. The two-word instruction is as same as one-word instruction. Shown in the figure, the first column represents a opcode which accommodate 8 bits and the 7 bits for source operand and next 7 bits for destination operand. As I told earlier, 7-bit identifies the addressing mode or the registers involved in it, and the 10 bits are used for the other information. As I told, the other information are referred to as a index value. So, what is the difference between one word instruction and a two word instruction? Other than opcode, source, destination and other information, two-word instruction can also accommodate a pull memory. Examples for the pull memory is and, hash. So, if the size is more, we have to make use of two-word instruction to store the complete operation. So for the instruction like move R2 comma location, we have to use two-word instruction. In encoding of machine instructions, a more powerful instructions would be, for example, add R1 comma R2 comma R3. So this operation performs R3 assigns R1 plus R2. Let's keep this one operation one side. Suppose if a 32-bit word length have 8-bit opcode, how many instructions can we have? And 16 registers in total. How many bits would be needed? So the operation R1, R2, R3 is the one problem and this question is one problem. Now let us deal another example if it contain location 1, location 2. So for all this we should use 3-bit addressing mode indicator. It means 3-word instruction just as one word, two word, we use 3-word instruction for this problem. So, in encoding of machine instruction into 32-bit words, this is the diagram which represents a 3-operand instruction. In encoding of machine instructions, if we insist that all instructions must fit into a single 32-bit word, is it possible to provide a 32-bit address or a 32-bit immediate operand within the instruction? So the solution for this question is yes. Yes, it is still possible to define a highly functional instruction set which makes extensive use of the processor registers. Let us consider an example. Add R1, R2. Yes, in this it is possible to define a highly functional instruction set. So in the example 2, add location R2. Here it is not possible because location is a one word and R2 is another word. This requires more space to accommodate, means it requires more memory bits. In another, add of R3, R2, here it is possible to define a highly functional instruction set. Here, R3 is used as a desired memory location. In encoding of machine instruction, how to load a 32-bit address into a register that serves as a pointer to memory location. So for this there is a two solution. The solution 1 is direct the assembler to place the desired addressing a word location, and the another solution is to use logical and shift instructions to construct the desired 32-bit address. So this means that by using the assembler we can place the desired addressing to a word location, and to construct the desired 32-bit address we can use logical and shift instructions. In memory, CISC. The full form of CISC is Complex Instruction Set Computer. By using CISC, we can use multiple words. We can implement complex instruction closely resembling operations in high-level programming languages. The term complex instruction set program CISC refers to a processor that use instruction set of this type. So the main idea is that a single instruction will do all loading, evaluating and storing operations, just like a multiplication commas will do stuff like loading data, evaluating and storing it. Hence it is complex. The characteristics of CISC is complex instruction, hence complex instruction decoding. Instructions are larger than one word size. Instruction may take more than single clock cycle to get executed. Less number of general purpose register as operations get performed in memory itself. Complex addressing mode, more data type. Let us consider an example for CISC. Suppose we have to add two 8-bits number. Then the CISC approach will be, there will be a single command or instruction for this like add, which will perform the task. Now RISC. The full form of RISC is Reduced Instruction Set Computer. The restrictions that an instruction must occupy only one word has to lead to a style of computers that have become known as reduced instruction set computer. The RISC approach introduced other restrictions such as that all manipulation of data must be done on operands that are already in processor registers. So the main idea of RISC is using an instruction set composed of a few basic sets for loading, evaluating and storing operations, just like load command will load store and a store command will store the data. The characteristics of RISC are simpler instruction, hence simpler instructions decoding. Instruction come under size of one word. Instructions take single clock cycle to get executed. More number of general purpose register. Simple addressing mode. Less data types. Pipelines can be achieved. So the example for RISC is, suppose we have to add two 8-bit number, then the RISC approach will be reduce the cycles per instruction at the cost of the number of instructions per program. Here there is a summary between CISC and RISC. CISC emphasize on hardware, RISC emphasize on software. CISC multiple instruction sizes and format. RISC instructions of same set with few formats. CISC less registers and more addressing modes. RISC use more registers and fewer addressing modes. extensive use of microprogramming. RISC, complexity in compiler. CISC, instructions take a varying amount of cycle time. RISC, instructions take one cycle time. CISC, pipelining is difficult. RISC, pipelining is easy. So to make this presentation on the topic of encoding of machine instruction, I have referred a textbook named Computer Organization by Karl Hamacher, and also even I have referred a notes of Professor Anand S. Hiremat, and some of the information I have referred from a Google. Thank you everyone for watching this video.